Okay, so we're looking at the relationship between two variables, looking at correlation and regression in chapter 4. So we often wish to study the relationship between two variables when each entry in a data set corresponds to one entry in a second data set. The sets are called paired data sets. So we're going to consider data from 2016 Major League Baseball that shows the salaries and average attendance at home games, just to see what paired data set looks like. So here is a salary and the average attendance per home game for different clubs. So there's paired data where the salary has a paired average attendance per home game for each of those different clubs. Another way we can look at the data is in what we call a scatter plot or a scatter diagram. So it's a graph that shows the relationship visually between these two quantitative variables measured on the same individual. So the salary is across the horizontal axis and the average attendance per home game is on the vertical axis, or the X and Y axis. And each individual is represented by a point in the scatter plot. The explanatory or independent variable is on the horizontal axis, and the response or the dependent variable is plotted on the vertical axis. We call it the explanatory variable because we think that may explain the response variable. So it is believed that the salary may explain or predict the attendance per home game. Okay. A correlation is a relationship between the two variables. So we have 4 pictures here of correlation. In the first, on the top left, the negative linear correlation, as X is increasing, so as our X value here is increasing, our Y value is going down and decreasing. Okay, so they start high and end low. So this is a negative correlation, and it's a linear correlation because it's a line. There are other kinds of correlation, but we're not going to do them in our class, but you can do all kinds of curves and all kinds of stuff. A positive linear correlation means as X increases, Y also increases. So it's considered a positive correlation because they're not opposites of each other. This graph is a graph with no correlation. You can't really see any kind of pattern in this data at all. This is a really strong pattern, but it's not linear. It's not a line, it's a curve. Okay? So correlation is just another name for the relationship between the two variables. The correlation coefficient is the measure of the strength and the direction of a linear relationship between two variables. The symbol R will be used for the correlation coefficient for the sample. So here's R, and that's going to be our correlation coefficient. The population correlation coefficient is represented by the Greek letter rho, or R, pronounced rho, and it looks like a P, but it's actually a letter R. We're not going to use that much, but I threw it in there. The correlation coefficient ranges from -1 to 1. So it's always a number between -1 and 1. It's a perfect positive, it would be R equals 1. So if it's a perfect dotted line, then R is equal to 1. If it's strong, so you can definitely see the shape of the line very easily, then it would be close to 1, but not quite 1. And if it's weak or moderate, then you can still see that it's an angle and going up from left to right. It's going up both directions. So it's a weak positive correlation. A perfect negative correlation has a correlation of -1. A strong negative will be close to -1, like -0.92. And then this one's just a mess, so it's got no correlation, meaning close to 0. So if it's got no correlation, it's going to be close to 0, either positive or negative. We're going to be using StatCrunch to calculate this because it's a big, ugly formula.
I actually have a question.
Yep.
For the two that are on the end, obviously the both of them don't have a correlation, so how do you tell the difference between which?
So this one has no correlation at all. It's really close to 0. This one you can kind of see that it's got like this shape to it, that it's going upward. You see that? It's not great, but it's there.
No, it's not.
It's there. So the way that you're going to know is you're going to calculate the correlation coefficient. But there is a thing in StatCrunch you can play with if you want to try guessing the correlation coefficient. Given how little time we have left in the semester, I wasn't going to assign it, but if anyone wants to play with it, let me know. So when we test for correlation, we're going to determine the number of pairs in the sample and specify the level of significance. That's similar to what we did in the last section where we said, you know, alpha equals what? And there's, if you look at the chart on the right, it's kind of hard to see, but there's alpha equals 0.05 and alpha equals 0.01. Those are going to be the two that we look at. And then you're going to go to the right sample size and just pick out the one that matches. And if your R is greater than the R in the chart, then we consider it significant. So the bigger the sample size, the smaller you require the R to be. Because it ends up the R is not very resistant, so one wonky value is going to really mess it up. So the more values you have, the less you require. So we're going to do an example of that next.
What did you just say? The more sample you have. What's that last thing you just said?
Sure. If you look at the numbers here, it starts from 0.95 and goes down 0.40, 0.30, 0.20, all the way down to almost 0.2. The higher sample size you have, let me write it. So the higher sample size, the lower the critical value required for significance. So that means you can have a lower R if you have a higher N. Because these numbers are lower that you're trying to get to be bigger than, where these you have to be pretty big to be bigger than them. So let's look at a specific example. So a study is done to determine the correlation between adult mother and daughter heights, and it's conducted with n equals 25, so a sample size of 25. And using StatCrunch or something similar, they get R equals 0.473. You don't think of 0.473 as great, it's okay. It's kind of in the middle between 0 and 1. So to determine that the correlation coefficient is significant or not, we're going to use the chart and compare it to alpha equals 0.05. So here's our critical values for alpha equals 0.05 and n equals 25. And that value there is 0.396 from the chart. Since our R value, 473, is greater than 0.396, then our correlation is significant. So that's how you're going to check. There's some questions like that in the homework. So how do we do this in StatCrunch? We're going to have two columns of data. The X's and Y's are together in a column. And you're going to do, oh, these are backwards. Stat regression is what we're going to do. So we're going to click on regression. So stat regression and simple linear. And what opens up is here. So this is number 1. This is number 2. You're going to pick which variable is your X variable. This is your explanatory. And which variable is your Y variable, which is your response. And you click compute. So you just have to look for the word regression. So there's a lot of output for this one. I'm just going to point out the one thing you need at this point, which is the correlation coefficient R, which is given, it's circled there. The correlation coefficient is 0.4907. Now notice I also circled that little arrow on the right, on the bottom. That, when you click on it, will give you your graph of your data. So this was a lot of data, obviously. Okay. So pretty simple to get your R value. And then you compare it to the chart. So let's talk a little bit about what correlation means and doesn't mean. Correlation does not mean that one thing causes another. It doesn't mean a cause and effect relationship between the variables. It could, so there are 4 possible things. It could be that X does cause Y. For example, there's a correlation between the hours in the tutoring center and GPA. Could mean that spending more time in the tutoring center leads to a higher GPA. That's a reasonable expectation. Or it could be the opposite. It could actually be that Y causes X. So correlation between hours in the tutoring center and GPA, it could be students who have a higher GPA tend to hang out in the tutoring center. So it may not be that one causes the other. It could be the relationship is caused by a third variable or a combination of several variables. For example, this is true fact. The number of shark attacks on Cape Cod is highly correlated to ice cream sales. Both ice cream sales and shark attacks are actually correlated to the temperature of the air and water. So it's not that shark attacks cause ice cream sales or ice cream sales cause shark attacks. They just both happen to come when you have, you're going to be more likely to have both of those happen when it's warm. And the second is it could just be a coincidence. So there's no other variable around. So for example, there's a strong correlation between the number of animal species in certain regions and the number of people who own 2 cars. Those are not related at all. There's no variable you can find that actually causes both. They just happen to happen together. So there's no real explanation for cause and effect. So the big thing we say in stats is correlation is not causation.